Okay, good afternoon. We start now?
Yes.
Right, good. So, okay, before start, wish you a happy Shivaratri, right? And we will, what I'll do is that in the first class, I will take it out. Second, I will close very soon by taking a small amount of time so that you can enjoy it. Okay. So in this lecture, we'll discuss about the blockchain. Of course, a blockchain is an interesting tool for building a trust systems. Right. Okay, that we'll discuss today. Right. So what I'll do is that I'll discuss about the blockchain, and I will take an application, a cryptocurrency application like Bitcoin. Of course, one should not think that the Bitcoin is only the blockchain. Okay, it is an application of blockchain, and the Bitcoin is blockchain means not only the Bitcoin. Okay, right? That confusion should not be there. Then I will discuss about some security and privacy issues, and I will touch some scalability issues also, where I will touch upon a particular tool or a particular mechanism, which is called the payment channel network or PCI, which is used in the Lightning Network for building for achieving scalability. Then there are what the security issues are there. I will discuss it out, and how those security threats can be mitigated. Also, we'll discuss it. Okay. Well, thank you. So look at this definition of the blockchain. How we can define it is that it is a decentralized computation and information sharing platform that enables multiple authoritative domains who do not trust each other to cooperate, coordinate, and collaborate in rational decision-making process. Okay. So, hope the definition, of course, I have stolen my carried out of this particular reference, and it looks interesting. If you say that it is a decentralized computation, and see that though in the decentralized computation many nodes are there, okay, because they are decentralized, and interestingly they do not trust each other, but you need to build a platform so that the application will be trusted. That's what I mean to say, right? So if you look at this, let's say that there are two parties, I would say that rather Alice and Bob would call it Aaron and Babita, right? Okay, just I changed it to the English names. Right, they want to create a shared document, like because today's day also we create these shared documents in the shared latex or overleaf or in the even in the your Google Docs, right? So what you do is that somebody will create a document, and you can change it out or modify it, and the other parties too can modify it, isn't so, right? But here, so this platform is centralized, right? As in the example of the Google or the owner of the overleaf or share lattice for memory, right? Here, it is not so, right? It is a decentralized network which is taken care of. That's the basic difference, all right? Clear? So rather than trusting that only one, if I trust one only, then there is a problem of the centralized failure. Okay, single point of failure, what you can say. If it is centralized systems, if today that one network like so Microsoft is not working or something else, then entire system got wrong, right? So it is not so. So that your system got now the more reliable. That's what I mean to say. Okay, right? Well, so each node, you see that there are different nodes, as I told you, in the system, in the blockchain system. Each node maintains a local copy of it. Okay? And local copies of every node is identical. Then, of course, it seems interesting, right? So, to see that what is requirement now? Everybody at a particular time, the state is same, right? That's what I mean to say. The local copies of every node is identical. Okay, clear now? And the local copies are updated always. So how it can be done? So it can be done by one body, one person, and everybody has to trust that. So accordingly, that everybody will update it out. So that is this trust system. So now, at the beginning, I told you that no one is trusting to others, but now I'm telling you how one will trust to. Okay, when you update, of course, it is updating it coming from somebody, some node, and it will broadcast it out. The other will update it out. But at the same time, they have to build a trust. Yes or no? So let's see, that is the most important things. That's what we call the consensus mechanisms. Right? Okay. As an example, that key, okay, let's say that key, we will decide to go to a hotel, and there are two different options of that. Okay. So many people are there that, okay, we will, whether we go to the IIT or we will go to the, what is it? We have thought, right? So where to go, right? So what will make it that, one thing is that, okay, somebody will propose it out, and other will give the vote. So the majority vote, I will count it out, and we will follow that. So that is its consensus mechanisms. Clear, no? Right. Similar things happens in the leader election also. But here we'll see the consensus mechanism in a bit different way. Today we'll discuss, I will emphasize to the proof of work, which is used in the Bitcoin. Because nobody is knowing to each other. There what everybody is here, so that I will ask that, okay, how many of, well, like I propose that we will go to the IIT, then I'll ask you to vote. Right. Let's say the n minus 1 people told that, okay, we'll go to the IIT, and n plus 1 people told that, we'll go to the Bihar fact. Then obviously the majority is n plus 1, so we'll go to the Bihar fact. That's the consensus, right? So then everybody has to go, right? So everybody is having a consensus that when the majority people comes, then I will take care of the majority. So whether you voted for that or not, it's the matter here. Like this we will do. So okay, we will not go to that. We will discuss in a bit how in the Bitcoin the consensus mechanism is achieved. That is called the proof of work. Okay. Well, so system ensures the consistency among the local copies, and the local information are stored in the form of a public ledger. Basically, the blockchain works like a public ledger. So the public ledger is just, can be visualized as follows. Like, I differentiate in this as centralized ledger, and the right side is the distributed ledger. You see what difference happens. In the centralized ledger is your bank, right? So everybody is having their passbooks, and corresponding to passbook, the information is stored in the bank, right? Okay. Now, assume that some transactions, okay, a mismatch or somebody else read it out, and he's claiming that, okay, what is written in my passbook is correct. Do you feel that the bank people will accept it? No. Therefore, say that the golden record is theirs, right? Whatever there, they will accept it out. So you need to maintain a reconcile its own ledger against that of bank, and must convince the bank of the true state. Okay. On the other hand, in the distributed ledger, it is not so. There is no centralized party like a bank, right? So each party is having you can say that the same role or same capability, right? Clear? So that we call each node is a peer here. No, nothing is the server and nothing is the client, or you can say that everybody can work at the client and everybody can work at the server too, right? So that is this. So there is one ledger. All nodes have some level of access to the ledger, and all nodes agree to a protocol that determines the true state of the ledger at any point of time. Okay, and the application of this protocol is sometimes called the achieving consensus mechanism. That's what I say. Make sense? Right. So how the distributed ledger works as follows: that user initiate a transaction using its digital signatures. Of course, next after this I will discuss a little bit of the digital signature. Then you just broadcast the transaction to the nodes. So I will create a transaction, and I will say I will distribute it to others. Means I will broadcast it that this transaction I made it out, right? And one or more nodes begin validating each transactions. How the validation I will tell you in the next slide, right? And nodes aggregate the validated transaction into the blocks. Validating in the sense, look at this similar example. When you do a transaction, let's say you want to transfer an amount of 1,000 rupees to your friend, right? Then what happens that the bank manager will check it. What he will check? Whether you have in your account more than 1,000 rupees or not. That is the basic one, right? That is validation. right? Once you have, then you check that whether your signature matches with it or not, right? You're given a check and you say that, okay, your signature matches and you have more than 1,000 rupees in your bank account, then he does the transactions, right? That's what I'm saying. So you validate the transaction, is a proper transaction, then notes aggregate the validated transaction into the blocks because it is, you can say that it is the single centralized server. So from your account, he deducted 1,000 rupees and your friend's account, he added it to 1,000 rupees, right? So here it will be done, but not in that way because there is no centralized party. So we'll create a block because each transaction will not broadcast it out. Okay, so the node has stored certain transactions. Again, once the sufficient number of transactions are there with him, then he will create a block. And node will broadcast the blocks to each other. Got it, fine? Right? So each transaction is not. So you created a transaction, you send to a node, nearest node of yours. Then the node, you will broadcast the transactions to nodes. Right? Node has not broadcast, right? Now one or more nodes begin the validating. So they validated it and then they kept it, right? Once a sufficient number of transactions they got it, then he will create a block and that block he will broadcast it. So then I told you that, so once one node is broadcasting a block, many nodes can do it also, but which is to be accepted. So that some consensus is to become, right? So that is the consensus protocol used, so that they will accept a block, and then block will talk in the two state now. So once consensus is achieved, now it can be a true state.
In case of multiple authority, but we are talking about blocks. Suppose it is a hierarchical order. So in that case, how we can do? If it is a maze kind of network or
you see here, this is it, right? So this is my notes now. And somewhere I have used, I created a transaction, right? And I give it to the node. I broadcasted it. Let's say A and B got it. So you'll keep it in, which is called the on-spent transaction output, UTXO. They'll keep it out, right? So once the nodes have a sufficient number of transactions, or they have some time limit to it. So either of these occurs, then they will create a block. Okay. For creating a block means just not adding the transaction, they will create the magic tree. That is one way. And after that, what they will do is that to get the consensus, that is proof of work.
Particularly that block.
Yeah, for that particular, for each block, they will, everybody has to do the consensus, right? Everybody has to agree that this block is acceptable. I'll show you in the next slide that what are they in the blocks, so how the consensus is achieved. So they will validate it out. If somebody could do it, or exactly he spent the sufficient amount of time for generating the proof of work, then they will respect to that. Because here there is no voting. The voting comes only if I know. I could see that, just like your permission blockchain. Then of course it would work out. Make sense now? Well, so then this is just the power of the distributed ledger. It can be used without a central authority by individuals or entities with no basis of trust each other. It can be used to create value or issue the assets. Then it can be used to transfer value or the ownership of the assets. It can be used to record those transfer of value or ownership of the assets. And it can be used to allow owner of assets to exercise certain rights to. So this is what a distributed ledger can perform, right? We'll see that the degree of trust between users determine the technological configuration of a distributed ledger, right? So this will keep it aside. We'll see that what happens here. See the public ledger of the banking applications, what happens? Let's the particular state, say Alice is having 100, maybe you can see that $100 or something, and it created transactions A to B 30. So it passed this, and you see here A to B 30, which is noted by each. Bob, I noted this, as well as Jack, which is not concerned with the transactions, but it also noted that A to B 30. Right? Then let's say sometimes after the Bob sends $50 to Jack. Then now you see that every node is maintaining that B to J, 50, and so on. Right. So here the validated it's correct. So let's say at some instance of time, if Alice again want to do a transaction which is more than that what she has, then that not be validated. So before let's see what is happening. So the time instance of I calculate the H of 0, the hash 0, Alice keeps it 100 and sign of Alice. Okay, and this is the initial state, true state, right? And then this is the H of 1 is the Alice to Bob with 30. What do you have this? Sign of Alice. So Alice signed it. Just like your check. I pay this amount and I sign it. Okay. Then Bob is given Bob to B to J, Jack, $50. So obviously B has to sign. Right? So then time instance of I plus 2, if Alice tries to send, say, 80 coins to Jack. Now see that what Alice says, Alice to Jack, 80 and signed by Alice. Because he performed that transaction. So the transaction is sent to the node. Now what happens? Once it comes out, he checks that, okay, Alice already given $30 out of what $100 he has. That means he has only $70. But he cannot spend $80. That means it is invalidated. Therefore, this will not come into that. Make sense now? So that's what I meant to say. So in a nutshell, I would say that the transaction is requested, then broadcast the transaction, then most importantly, the transaction is validated. If it is validated, then it will be added to the block. And the block will be added to the blockchain. So the blockchain is actually not a new concept. Previously, if you look at the 1982 or something, that Harvard and Somanath, they published a paper for hash chain mechanisms. This is a similar concept is used in the blockchain, of course. Okay. There is a chain of blocks that contain the data, and first block in the chain is called the Genesis block. Just as the beginning we say, right? Okay. Each new block in the chain is linked to the previous block. So here it is not the linked list what we discussed in the data structure, but the concept is more or less similar, right? In the linked list, what are you doing? We're keeping the address of the previous node or address of the next node, what you say. Here what I will do is that for linking, I will keep the hash value of the previous node. So therefore we call it hash chain. It is also the linked list, but we call it hash chain of the hash values, right? So each new block in the chain is linked to the previous block. Make sense? Well, so data show depends on the type of the blockchain. A Bitcoin block is having this like data like the sender, the receiver, amount to be transferred, and that is in the number of Bitcoins, amount to be transferred. Okay. So each block contains data, hash, and hash of the previous block. So as just I told you, let's say this is the block H is equal to 236. Okay, and previous that's I would say that 000. I call the first block, I would say. Next block, when I calculate that H is equal to 748, which is containing the the data, this H, the previous hash value 236. And so on and so forth. You see the next I kept H is equal to say 986, but while calculating this H is equal to 986, the previous hash value is included here, this 748. Make sense now? So then what will happen? Actually, why you keep the hash? You said that if I change a value here, then this hash will be changed. Now, if this hash is changed, let's say I change this some data is there, said 0, I made it 1, then this H value is equal to 748. It is changed now to maybe 243. So then you see here I should use the 243. So because it is not 243 but 748, if it becomes 243, if I make, then this will be changed. And so on, this chain will be changed. Right? So therefore it is immutable. It's difficult to mute. Make sense now? Okay. Yeah.
सर जैसे कि ब्लॉकचेन में नंबर ऑफ नोड बहुत ज्यादा है, डिस्ट्रीब्यूशन फैशन में है, तो अपडेट होने के लिए जो उसमें लेटेंसी इशू नहीं होगा?
होगा. We will come into that. Sure. Latency होगा नहीं होगा? कैसे नहीं होगा? Right? So we'll see that for getting the if the latency is there, then what is the problem? Right? There is chance of the double spreading. Okay, we'll see that. Right? Okay. There will be, but we'll see that how the actually we're giving such time so that that block will spread entire network. So all nodes know it now. Okay, right? We'll come to that, right? Sure. So therefore, what I told that why the has now changing a single block can quickly make all following blocks invalid. Yeah, right. So blockchain uses a distributed rather than a central entity. When someone joins the network, it will get full copy of the chain. It will get full copy of the chain, right? So each computer is called the node or peer, which works as this client as well as server. So we call it the peer, right? And it looks like this way, right? So this fellow, 1, 2, 3, 4, all the nodes are having this because they have the nodes. So now if sometimes one block is added, I just told that it is added to here, then same block is to be added everywhere. Then only it will come into the two state, right? So to make these things, we have these consensus mechanisms. So after complete checking, each node adds this block to their blockchain, and all these nodes in this network create a consensus. They agree about what blocks are valid and which are not. Make sense now? So to temper, one needs to temper with all blocks on the chain. Okay? Okay, all blocks of the chain, not only that, redo the proof of work for each block. Okay, right? Take control of greater than 50% of the peer-to-peer network. Well, majority has to agree, right? Right? So that's what is called a 51% attack. Right? So yeah. So here you see that what I told you that okay, I have in this slide. I'll tell you that how the proof of work comes. Right? So these are the different categories of the blockchain: public and permissionless, which is your Bitcoin and Ethereum comes in this category. And others are with the Ripple and US are the public but permission. Okay, you require permission to join, right? And here this is the private and permission. You require permission to join. There are some are there in the private and permissionless, but it is not in worthy. So I kept it the question mark here, right? Okay. So Bitcoin is a completely decentralized peer-to-peer permissionless cryptocurrency put forth in 2009 by what you can say the anonymous author Satoshi Nakamoto. Completely decentralized, no central party of ordering, or recording, or anything. Right? It is peer-to-peer and permissionless, so that no identity, no need to sign up anywhere to take part. Anyone can take any rules. That's it. Okay, anyone can be miner, right? If you have the power. So blockchain size of Bitcoin is of course 306 GB as of 2020. Now I have to check the net, of course. All right. So see what is happening. This is a sequence of blocks headers of 80 bytes each. So each block header is of 80 bytes. Okay. What are there? Just I wrote it now that it is having the version of 4 bytes. Previous hash value, which is 32 bytes. Right, that is 128 with hash, right? And the time of 4 bytes, bits, which says you that the difficulty of the proof of work, right? And the nonce value and the transaction routes. These are the transactions. So only the transaction route is there. So what is that route? It is a market tree. So all transactions are there in the at the leaf level. And if you take the hash of this is, and take the hash of this is, and take the hash of these two, this, and so on and so forth. This will be your route. So make sense now? right? So once you read it out and get the transaction root, and the total is my 80 bytes. Okay, so it is digitally signed and encrypted transactions verified by the viewers. Digital sense means who generated the transactions, I need to sign it. Okay, well, if you just see that how do you transact? You have a money, right? Let's say you have a 100 rupee note. Are you signing when you are giving to somebody? No. Why? Just to correlate it? Correlate it. Why you are not signing? Because there is a trusted party. Governor is signed there. And they see that it is written that I promise to pay this 100. So it is with whom it is promised of the governor, right? That is, this amount will be given to you. So it is not required. Make sense now? But here it is not so, right? As I told you that I took some amount and digitally, which is called the unspent transaction output. And when I want to give it to somebody, then I need to sign it. And then see that if I take that, let's say A is given some amount to B. So this is digitally available. Can C use that amount? You see that? Just let me contradict here. I have a 100 rupee note and somehow you took it out. Okay. If you give to another person, will he object? No, it is Somanath's account. Or it is Somanath's money? No. Right. Why? Just as I told you that. There is no guarantee that it is mine or nothing else. Who is having that it is his. Right? Because it is sign of the governor. Right? But here in this case, when that Bitcoin comes to me, everybody is looking at, right? Anybody can take it out. Will it be anybody's? No. So it will be given to me in the sense, it will be with my identity, my public key. So I have the corresponding private key, so only I can use it. Makes sense, huh? I need to prove that I am the owner of that because I have the private key. Then when I give it to another person, I open it and I'll say that, okay, this is of his. Makes sense now? So we have the in transactions and out transactions. In transactions, I'll say that these are the transactions I have. I collected it from the A to me, B to me, and C to me. And I combine it together and I say that, okay, this amount I given to D. Okay. And see that if you go by a taxi, it is 75 rupees and you give an 100 rupees note. Then what will happen? Will you leave him? No, right? He will give you 25. You have to ask him, right? And similarly, as I told you that the A has given me 9 rupees, B has given 3 rupees, C has given 10 rupees. So 9 plus 10 plus 3 is total 22 rupees I have. And if I want to give somebody, say 17 rupees, then I need to take 5 rupees, right? So while do the transaction output, so in is this 3 and out will be this 2. That person 17 and mine is 5. Make sense now? So this is what I will do. Okay, right? So the cryptographic security that ensures that participants can only view the information on the ledger that they are authorized to see. Okay? And each block contains 2 parts, the header and the data. The data means the transactions, right? The header of a block connects the transactions. Any change in any transaction will result in a change of the block header. Why? Can I say it out? See now here. So I told you that these are the transactions, right? So if one transaction is changed, then what happens? This root will be also changed. Because this is the host of this. Then again host. And so on. So obviously this root will change. If the root will change means syntax will change. The host will be changed, right? That's what I meant to say. Right? The header block connects the transactions. Any change in any transaction will result in a change at the block header. Make sense? Header of subsequent blocks are connected in a chain, just as I told you. Whole blockchain needs to be updated to make a change anyway. Okay. So just what we discussed on the permissionless. So no identity while participating in the consensus systems. Even you can join in the Bitcoin systems, create your own wallet and do the transactions, right? No participant in the network really knew all other participants. You cannot know. You don't have any trust, right? consensus to be achieved when the network is arbitrarily large. Okay, this is the challenge now. So what happens? You have to have some other mechanisms, right? So the most appropriate mechanism is challenge response by systems, where the network will give a challenge and it need to respond it. So what the challenge is that, and each node in the network tries to solve this challenge. So who could solve that challenge is the winner of that. Okay. Now see, mark the things. What is there? You say these are the things common, right? Everybody is having this. So to create a block, that I will hash it out. Okay. So when you hash, see, I'll get a digest value, right? So what the hash does? Hash takes an arbitrary length input and output a fixed length. And it is one way. From that fixed length, you cannot get the input. That's the property of the hash function, right? Here, what they constant is that you hash it out, and the network, given the challenge that your hash value should have, let's say, first 10 digits are 0. Okay? First 10 digits are 0. Then what will do? You cannot do anything, right? So what the things you need to change is something so that the first 10 bits, the MSB 10 bits, you need to become 0. That is your nonce value. So I'll test it for the nonce is equal to 0, nonce is equal to 1, nonce is equal to 2, and so on. There is no other. So for this, a huge computation you will require. So who has that huge computation and who wins that race, he will be winner. That is my. And nobody will do, it is no free lunch, right? Nobody will do that. He has to get some amount, right? So he will get the amount for this minor fees, right? In addition to that, for each transaction, there will be an amount for the transaction fees. So all the transaction fees and computing this mining, these things will be of that particular person or particular node who will. Make sense now? The mining, of course, the minor fees, they made it like this way. The minor fees is changing for each 4 years after some certain transactions and so on and so forth, right? Well, so obviously to get that fees, it is a race, right? Who will win that race? So who would form that block? He will winner, he will take, and that is called the coin-based transaction. Therefore, I kept in a different color than this. These are the transactions that I told you that A is giving to B or B is giving to C, all the things. And this is the coin-based transactions, what he will get. Make sense? So that, now, a challenge posed by the network, just as I told you, challenge is that let's say this many number of zeros are there, or your hash digest is less than a particular value. Okay, this is the challenge. So if it can proof of work, this is called proof of work, and shows consensus over a permissionless setting based on this challenge response. Okay. So the consensus algorithm, any consensus algorithms must be fault tolerant. That means if some nodes will be unavailable when the ledger is changed, it could happen also, but your system should work, right? And consensus should be reached by part of the nodes or majority. And attack resistance, some nodes will intentionally behave incorrectly. It could happen maliciously. Honest nodes should win the consensus process. Okay. Everyone on the network can verify the next block's correctness. One will generate, but anybody can verify. Anybody can see that, okay, whether the hash is correct or not, and this many zeros or not. It's very simple. Or whether this result is less than this or not, right? So anybody can verify it. Clear? And it is simple task. Therefore, I tell everyone can do it. But for doing that, you require a huge computation. Okay, makes sense? So too much resources should be required for a successful attack. Well, so we'll see the attack taxonomy of Bitcoin. There are several attacks, of course, there. I split it into just today that few attacks here. That is the denial transaction attack, double spending attack, eclipse attack, approved Bitcoin mining attack, 51%. I already told you that. Selfish mining, malware attack, and so on and so forth. Right? So this is due to end the blockchain design. It could be at the P2P architecture level. It could be due to the consensus mechanisms. It could be at the transaction level. Right? So let's summarize the things what we discussed before going to the attack. That if I look at the Bitcoin transaction, just I told you that half of the previous transaction we have and new owners public. So let me give the same example. Let's say somebody given me some Bitcoin. So it is from A to
This is IIT.
A to S, right? This is and it has a previous transactions, that is that, and the new owners public key, my public key of S, right? And when I give it, I need to do the transactions, right? So what I'll do is that I will sign it out. When I sign what's required, my private key. So this indicates that I'm the owner of this. Okay? This is the new owners public key. So now I sign it out, I given it out, right? So as an example, that check I given it. So pay this amount to this person, to this account number. And in between, I'm signing down, I'm signing it out. Okay, so the bank manager see that my sign is okay, correct? And to whom I'm giving. Okay, that is this. So he will transfer that account. Clear now? So when it goes to that person, again he will do that. This is this. So he will sign in his own key. That means it's the private key is corresponding to this public key when he was using. Okay, so therefore this public key is of the new one who will use this transaction. Makes sense now? Clear? So the pair choose the coins where each of the chosen coins was spent as inputs to the transaction, and the public keys, that the address of the pair, are then used as outputs of the transaction. Okay? Each pair verifies the transaction. The same coin has not been spent twice, and the coin is valid from the correct previous pair. Okay? Because in this previous transaction, my public key was there, so you'll see that okay, this is matching, it is mine, and I'm giving to this place, this fellow. So the same things will happen with that person also. Okay. So the attack would be at the starting from the lower level, that denying the delivery of the transaction. So each node will check that once transaction happens, they will verify that okay, one transaction came, so that they will put in the block, right? So see, the transactions are propagated using an advertisement-based request management protocol, which is called the inventory message, IMV message, right? So once the new transaction comes to the A, then A will send an inventory message to the node V, okay, broadcast. Then they will ask that, okay, get data. Okay, this is it. Then he will send these transactions. Okay, right. Now what attacker can do is that he will first announce a transaction that he says like, okay, I got the new transactions. Making the back-to-back a number of IMV messages, inventory messages, right? When victim send the get data A to A will not reply. He'll keep quiet. Right? Okay. So he sent the message, so he assured that okay, some transaction occurred, so he requesting that, oh, give the transaction. Right? Then he keep quiet. He's not giving. So what this fellow does, okay, he's not responding, he'll ask the other peers and so on and so forth. Right? He's not responding, so he'll ask to other people. So what happens? He will be busy with by doing these things, right? So if request for a given transaction is not delivered in 2 minutes, the next peer in the list is queried. So we'll query the next peer. What are you doing? When victim sends get data A does not reply, victim approaches to others which two don't reply as they don't know about these transactions. So they will not reply. And he will be busy with this, right? So deprives the peers from the benefit of immediately receiving and verifying any transactions. Because he is busy in doing this. Okay. Another thing is the interesting attack is the double spending attack. It is quite visible that you have a transaction and this transaction you are spending twice or more than once. Okay. If you have 100 rupee note, you can spend once only. Okay. Why? Because the physical note, if you give it to somebody, you don't have anything. So you cannot do it. But if it is computerized, so this transaction can give a copy and give it to somebody, and then again after that you will give it to somebody. That's what you ask, right? If the other people are not knowing that the transaction has happened, then obviously this will be successful. Right? So that's what he's saying. Okay. So what the people, let's say you do a online transactions and get some items from there. Right? So that fellow, what he will do, that the vendor, he will wait for that transaction, let the transaction comes to the block. Okay. And he checks that, okay, not only one block, let at least 3-4 blocks come out, then one cannot, it is immutable. So he is spent to me only. Then he will give you the outside. Make sense now? That's the things, right? So that's what he told. Because it requires the time. He told that it is a vast network. Then the transaction has to reach to all. When it is, now block is framed. So I need to wait sometimes till the block has come to all. Here now, right? So once it is coming to the true state, of course your blockchain is now reached the true state. So now we cannot make another transaction. Okay. So by that time it is already there everywhere. So that is called the true state. Okay. So what happens if 2 miners produce a block at almost the same time? Okay. There is possibility, right? The 2 miners can have the same block, can have a block at the same time. Maybe the 2 different blocks, right? Having the 2 different types of transactions, right? But at the same time. Then which block is to be considered? Now, at some times you will have a, you can say that the blockchain, the chain, like this way, and another time. So it is bifurcated now. So we will consider the longest chain, and that will be the true state. And this will be the longest chain represents the accumulated computational power of the network. Makes sense? Now, the 51% attack, just as I told you that the 51% is 50% measurements, half of that. So if I can capture the more than that, then of course I can do anything else. Of course, just 2 years back something happened and they told someone to come out from that. Okay. So I will try to catch up to 3 blocks and rewrite the history of the transactions. So what I can do is that, so I think I have it next, this is prevent transactions from gaining any confirmations, prevent people from sending bitcoins between the addresses, and reverse the transaction that happens when they generate the blocks, where the entire thing is controlled by them, right? So it cannot generate new coins without following the proof of work protocol. Okay, it cannot steal the coins from Bitcoin addresses because the private key, the corresponding private key is with the lying with that particular user only, right? And in fact, any past blocks are changing any transaction recorded in them. It cannot affect. Okay. So what the another attack is that is selfish mine. So they will do the mining, create the block, but as I told you that if the block, which is the longest length, that will be considered. So we will do it privately without publicizing it, After a while, when they make it a bigger one, then they hide it. So that is called the selfish mining. The attacker will mine his blocks privately and release them at the right time so that the honest miners host their computational power. So actually these attackers, right? They have not shown it out, that fellow. And once they build it out and added these things, right? Yeah. Another is the eclipse attack. So eclipse attack, of course, it comes in the network level that so that the packets will not, the packets will be all the blocks, right? It will not come across a particular range, right? So it will be only in that range. So that side will be called the eclipse, right? In that eclipse attack. So they cannot know what the operate happened here, right? That's what I say. So monopolism of all connections to and from a victim Bitcoin node. So adversary controls sufficient number of nodes off path, and the attacker controls the contiguous range, of course. Then it could be possible. Make sense? So these are the things. If you can do this, of course, this also can be done. Right? Why? Just what you asked. This is related to that, right? You made the eclipse attack, or if it's a vast network, your block has not transferred to that particular section. So I did a transaction in this subnet, and I will do a transaction to that subnet. So you cannot understand that. So double spending could be possible. Similarly, selfish mining is possible, and adversarial false is what I told you, that right? So it can generate the false too. Okay. Oh, yes, coming. Well, now let's see the key privacy issues. This is what you see, that the security issues. We discussed that. What the difference in privacy? It is self. Okay, it is user related things. So now we see that the user has many Bitcoin addresses. Please look at this, right? So it is the privacy guidelines is that you change the address frequently, but it is not infinite, right? Okay. So LSA can have many addresses because creating address is free, right? It is also, you will create your own public key and private key, keep the private key with you, and send the public key to somebody who will do the transactions. Right? So
जैसे गूगल पे वगैरह का ट्रांजैक्शन होता है सेम वैसे, जैसे उसमें भी 4 या 6 डिजिट का अपना पिन कोड डालते पिन वगैरह, लाइक वैसे सेम यहाँ पर भी।
No,
उसका डिफरेंस है।
yeah, it is different. Google is giving you just like a OTP like this, right?
Yes.
That who is creating that? Google is creating that. Right. He is authenticating that whether you are there, it is your device, then you are giving that. This is one-time password. It is not having with the public and private key concepts, right? But here it is the public key and private key concepts. That means I will generate the public key and private key pair. I will share the public key to you so that you will do the transactions to me. And I know that my private key so that I can use that transaction. Make sense? So this is the thing, right? Else can have many transactions like this way. See here that A1 that I have the inputs, that's I told that 4 plus 5 is 9. So I need to give to B 6 amount. So remaining 3 I need to get back. That is my A3 address. So this is my 2 addresses, A1, A2, and this is my 3rd address. So what you can understand here? Now obviously you are giving to the B, right? So B can know your 3 addresses now. Is it not? Right? B can know your 3 addresses. Right? That's what I'm saying. So these are the Alice address and that is the Bob address. This is the change address, of course. It could be here, right? This is the. Well, so now the question comes that whether Bitcoin is anonymous. Even though if you look at the privacy guidelines, user has many Bitcoin address, whether it is anonymous. No, absolutely. The Bitcoin is pseudo-anonymous, right? It is not anonymous. It is possible to link all addresses of a single entity. Okay. So given the two transactions A to B and C to D, are B and C the same? I can find it out. There are two transactions. We can find out whether the B and C are the same. If D knows C, and I know that B and C are same, one person's two transactions, as it happens here, right? Right. So I know that okay, A3 and A2 are same. I know that the A2 is of Alice, so that I can understand the key. Okay, A3 is also Alice, A2 is also Alice. So by knowing one, I unmask others. Right. So as an example that I given these things that buying a book from merchant. You bought a book from merchant. You spend these two, A1 4, A2 5, and given this B, that the bookseller 6 and yours is 3. So the bookseller is now knowing all the 3 addresses of yours. Okay. And somehow if I could link, then I can link all. Right? Of course, if you know your customer, etc., then obviously you can link the things, right? So it is not anonymous and it is linkable. Okay. So this is the trust issue of the blockchain. We discussed a few of the attacks, security and privacy threats, and it is the bunch of course I copied it from this paper for your notes. Okay, a huge amount of I can say that the different types of security and privacy threats over the blockchain. But anyway, it is not so possible attacks, of course, right? It is theoretical. Most of the things are the theoretical. Right? Any questions here? No? Right. So the trustworthy blockchain, you see that if I look at the blockchain key features, right? We saw that the append-only data structure. Right? If you look at the chain, you cannot insert in the middle of the chain. Like in a linked list, you can insert at the middle. It is not possible, right? Okay. So it is the append-only data structure. So you can append at the end only. All right. And it has chain because each node contains the hash value of the previous block. Okay. The consensus mechanism is there. And once it is done, the data is not immutability, right? And the decentralization, right? These key features, a trustworthy blockchain must address the following: the security, that protection against the attack like 51% attacks, right? Integrity, that is preventing unauthorized data modifications. Okay, it is immutable, so you cannot change the data once it is placed in the blockchain, right? Decentralization, so no single entity controls it out. Okay, and transparency, the transactions can be verified by all participants. Okay, right? Then the two issues that we discussed: the scalability, then the ability to handle increasing transaction loads efficiently. Okay, and the privacy and compliance, ensuring user privacy while meeting the legal requirements. Okay. Yes, come. Jag. Okay. So I'll stop it here. I'll continue from this, and after the T, and then I will talk about the PKI, trustworthy PKI, and maybe 40-45 minutes. Then I will give it up. Okay. Thank you. No,